Hello friends, welcome to GT Science tutorial. In this video, I'll explain the Le-Chatelier's principle. This is the third part of the chemical equilibrium chapter. In my previous videos, I've already explained about the basic introduction of chemical equilibrium and the laws of mass action. So let's start. So what is the Le-Chatelier's principle? So Le-Chatelier's principle is just like the self-adjusting rule. Okay, it is just like the self-adjusting rule. That means there will be an equilibrium condition and a perturbation is applied or the equilibrium is disturbed and the system will again come to an equilibrium. That is self-adjusting rule. Okay, so this is the definition of Le-Chatelier's principle. Look at here. When a system at equilibrium, so the system should be at equilibrium, is disturbed, that is a perturbation is applied, okay, by a change in temperature, pressure or concentration. So the equilibrium should be disturbed either by the change of temperature, pressure or concentration. Then the system adjusts itself to counteract that change and restore a new equilibrium. So this simply means that suppose A plus B giving C is a reversible reaction and at certain temperature, pressure and concentration, this system is at equilibrium. Now, among these three components, one of them is changed. Either the temperature is changed, or pressure is changed, or concentration is changed. Then the equilibrium of this system will get disturbed, right? The equilibrium will get disturbed. Now, after certain time, the equilibrium will again retain itself. Okay, it will again retain itself. So this is called Le-Chatelier's principle. After the change in temperature, pressure and concentration, the system adjusts itself to counteract that change. Okay, I hope you understood about the Le-Chatelier's principle. So in short, the reaction will shift. The reaction will shift in a direction that reduces the disturbance. So in short, we can simply say that Le-Chatelier's principle says that the reaction will shift in a direction that reduces the disturbances. So the direction in which there is less disturbance, the reaction will shift in that direction itself. Okay, I hope you understood what the Le-Chatelier's principle is. Now let's move forward. So let's understand the Le-Chatelier's principle with an example. Okay, the example is not very hard. We'll take the example of Haber's process, that is N2 plus H2 giving what? NH3 plus heat. So in Le-Chatelier's principle, some heat is released. Okay, this is gas. Hydrogen is also gas, ammonia is also gas. Now to balance this reaction, we need to put 2 over here and 3 over here. Now, what kind of reaction is this? This is a exothermic reaction, right? Exothermic reaction. Exothermic reaction. Now what if the temperature, pressure or concentration is changed? So among one of them or all of them it changed. Then what will happen? Obviously, the equilibrium will change. The equilibrium value Kc will change. Equilibrium constant value will change. Now after certain time, this constant value, a new constant value will be formed. That means a new equilibrium will be established for this reaction at the new temperature, pressure and concentration value. Okay, that is called Le-Chatelier's principle. Now let's see one by one. Now let's see one by one about the factors affecting the equilibrium, that is concentration, temperature and pressure. Okay, so how does change in concentration affect the equilibrium of the reaction? Let's see that. So if you add more of a reactant or product, so if the reactant or product is added, that is the concentration of reactant and product or reactant or product is increased, the system will try to use it up. The system will use that reactant or product. Are you getting me? Addition of reactant and product will increase the chances of the reaction, right? So you can see the 3 points. You need to remember this. Okay, so in the previous reaction, what was the reaction that we considered? We considered N2 plus H2 giving what? NH3. Okay, NH3. We are talking about concentration change only, so we have not written heat energy over here. Okay, so you can see if more and N2 is added, if the concentration of N2 is increased, then there will be more reactant, and as a result of that, more product will form, right? So the shift will be toward the forward, that is toward the right direction. More NH3 will be formed. That means increase in the concentration of reactant will shift the reaction in forward direction. Similarly, add more ammonia. So if ammonia's concentration is added, then what will happen? The backward reaction will increase. More N2 and H2 will form, right? So see, you can see over here, if more ammonia is added, then the equilibrium shifts backward. That is, more N2 and H2 are formed. Similarly, if ammonia is removed, then to replace this ammonia, more N2 and H2 will react. So the reaction will again go in forward direction. I hope you understood it properly. Okay. Now let's see another factor, that is change in pressure. That is only applied for gas, not for solid or liquid. Okay. Now for this we see the number of moles formed. Okay. In this reaction, in the reaction we talked earlier, when we balance them, then you can see 1 mole of nitrogen is reacting with 3 mole of hydrogen, forming 5 mole of ammonia, sorry, 2 mole of ammonia, right? I have written that over here. Okay, so 1 mole of nitrogen is reacting with 3 mole of hydrogen to form 4 moles of gas, right? So this is in the left side. Okay, 1 mole plus 3 mole is equal to 4 mole. 3 plus 1, 4. In the right side, that is N2 plus H2. N2 plus H2 giving NH3 to 3, right? 1 plus 2 is 3 in the left side. In the right side, what is the number of mole? That is 2. 2 moles of gas is present over there. So we can see the number of moles of the gas is decreasing in going from left to right, right? The number of mole is decreasing, and from going from right to left, the number of mole is increasing, right? Okay, so if you increase pressure, if the pressure is increased, then what will happen? The system shifts forward. The system will shift forward. The reason for that is number of mole is decreasing. If the number of mole is decreasing, the pressure should be increased to maintain the pressure, shift forward to form ammonia, fewer gas molecules, right? Similarly, if we decrease the pressure, the system shifts backward. If the pressure decrease, more amount of gas should be formed, and more amount of gas is in the left side, so right side reaction will shift to left side reaction. That happens in change of pressure. Similarly, in change of temperature, what happens when the temperature is changed? Look at here. So this depends on whether the reaction is exothermic or endothermic. So it is specific for exothermic or endothermic reaction. Okay, so we have considered this reaction, nitrogen plus hydrogen giving ammonia plus heat, that is, this is an exothermic reaction, right? So in this reaction, if the temperature is increased, so the extra heat should be absorbed, right? So the reaction will shift in the backward direction. If the reaction was endothermic, if the reaction needed heat, then increase in temperature would favor the reaction, and in that condition only the reaction would move to the forward direction. Okay, so in case of endothermic reaction, increasing temperature is favorable. Similarly, in case of exothermic reaction, decreasing temperature is favorable. Okay. Now, effect of catalyst. This is not among the 3 components, but effect of catalyst is very important to understand. Okay. So, effect of catalyst do not have any effect on the shifting of the equilibrium. Okay. It can only help to attain the equilibrium faster. That's what I have written over here. Catalysts do not affect the position of equilibrium. It does not affect the position of equilibrium. They only help the system reach equilibrium faster by increasing the rate of both forward and backward reactions equally. So the use of catalyst is to get the equilibrium faster only. Okay. Okay, so this is the summary table. If you understand this summary table, you understood Le-Chatelier's principle. Okay, so you can see change applied, and what is the consequence? That is the system response or shift, in which direction the equilibrium will shift. Okay, if the reactant is added, then the system will shift or the equilibrium will shift to product side, that is forward. Similarly, if the reactant is removed, if the reactant is removed, then what happens? The reaction or the equilibrium shifts backward, right? Similarly, if a product is added, then what happens? Backward. If product is removed, then again the reaction shift forward. Similarly, if pressure is increased in terms of gas, we only talked about a gas for pressure, right? If pressure is increased, then a fewer gas moles should be formed. If pressure is decreased, then larger gas moles should be formed. Okay, so that's what we have written. It shifts to fewer gas molecules, shifts to more gas molecules. Okay, similarly, if the increase in temperature, that is, if the temperature is increased, then shifts to absorb the heat, right? If the temperature is decreased, then shift to produce the heat. We have already understood that in previous slide. Similarly, if the catalyst is added, then the equilibrium will not shift, but it will help the it will help to attain the equilibrium faster. That's it. Okay. Now, finally, the real life example. You must have seen a soda bottle. In a soda bottle, there are soda fizzes, right? You must have noticed soda fizzes when more and soda fizzes more when you open the bottle, right? When we open the bottle, suppose this is a soda bottle, and if we open this lid, there will be a lot of fizz coming out, right? Because the pressure inside is greater than the pressure outside. Okay, pressure inside is greater than the pressure outside. Now this helps to as the um, wait a minute. So carbon dioxide is maintained, carbon dioxide is present in the soda bottle, and that is in equilibrium with the carbon dioxide aqueous form. Okay, there will be gaseous carbon dioxide and there will be aqueous carbon dioxide, and the bottle, when the bottle is open, there will be change in pressure, right? Pressure is decreasing and more carbon dioxide are forming, so that will escape out. Okay, so this is the real life example of Le-Chatelier's principle. Inside the bottle, carbon dioxide gas is in equilibrium with dissolved carbon dioxide, that is CO2 aqueous. Now, when we open it, pressure decreases, outside pressure is low, equilibrium shifts, more CO2 comes out, that is fizz is produced. That's what happened in a soda bottle, right? Now, this is a practice question for you. Okay, if you understood the video, please try this question and write the answer in the comment section. Okay, for this reaction, that is sulfur dioxide plus oxygen forming sulfur trioxide, the reaction is already balanced and it is giving out heat. What will happen if more sulfur dioxide is added, if the temperature is increased and the pressure is decreased? So what will be the effect of these things on this reaction, that is on the equilibrium shift? Okay, just write the answer and comment it in the comment box. Okay, I'll see the answer. That's all in this video. If you like the video, please share this video as much as you can, and don't forget to subscribe the channel to make me happy. Bye bye.